Hello. Hello, everyone. Can everybody hear me? Hello. Any feedback? Hello, hello. Okay. I think we should start now. And well, today we are going to discuss a little bit more about group theory. Looks good. So I think this looks a little bit better. If it doesn't, let me know. Okay. Well, today, let's discuss a little bit more about the group theory. And this is, I think, should be the last class about the group theory in general, which means later in next week, starting from next week, we are going to discuss about some, very special type of group and discuss how we can study this kind of groups. Okay. Maybe besides that, we also need to, by studying this kind of group, we also need to study some kind of like group action. How can you use a group to acting on some kind of set? Like, how can you use group action to play with the magic cube or to play with those kind of things, so-called 15 puzzle in your textbook? So we are going to change a little bit about our syllabus, about the stuff we are going to learn. Okay, but basically you can just follow the syllabus and I'll let you know what we are going to discuss. The only problem is you may not be able to do some preview before the class, so I will try to make it slightly easier and more accessible for you, for all of you who haven't learned anything, who haven't done any preview about it. Okay, so we'll see. And again, I'm open to suggestions. If you have something in special that you want me to discuss, then you can just let me know. Because after today's class and maybe one class next week, we are going to stop discussing this general group theory and discuss some kind of special type of group, like zero group, like free group, like finite generated abelian group, like whatever. Okay. So let's see. Last time we mentioned what is coset. What is a coset? If I gave you a group and then you can give me some subgroup of this group, and then based on this subgroup, we can divide the whole group into a lot of well, different parts, and this is H. This would be the coset of H, A times H. This might be B times H, this might be C times H, and so on. Okay, and we know that this kind of way, by studying this coset of a subset, is helpful because it can help us do something like a counting the number of the element of a group. Okay, today, first we will try to use this kind of coset language to study some classification of very small groups. Okay, as I mentioned last time, classification of groups are very important in terms of the group theory. The main thing this group series, the mathematicians who are interested in group theory are trying to deal with those kind of classification of groups, which is why you may always see some very fancy theorem about some particular type of groups. Okay, and our theorem say that, well, if we know that the group has element less or equal than 7, then we have this group is either cyclic, which is a group generated by, well, one single element, if the order of the group equals to 2, 3, 5, 7, the prime number. Okay, and of course, if G only have one element, then G is equals to the identity element, right? Only one element form a group. And G is, well, now 2, 3, 5, 7. Now the only thing that left should be 4 and 6. Then if the order of G is 4, then G is either Z4, well, as an addition group, or Klein 4 group. Okay, and we mentioned what is a Klein 4 group. Klein 4 group contains 4 elements, E, A, B, C. And A, B, C is an abelian group. A squared equals to B squared equals to C squared equals to E. Everything are just of order 2. Okay, and AB equals to C, BC equals to A, CA equals to B. It's more or less like a simplification of the Quotient group. Okay, or if G has order 6, then G is either, well, again, Z6, which is again under addition, and Z6 is, well, both Z4 and Z6 are cyclic group. Okay, and in the future, if I didn't write anything, just write Z4 or Z6 or ZM, I simply say that this is a group with addition. This is a cyclic group with addition. Okay, I will not write it like this. I'll just write Z6. Because for multiplication group, it's ZM is very complicated. The multiplication group of ZM is very complicated. Maybe not very complicated, but it's different from Z6 with addition. Okay, and then, or G is well, symmetric, well, is isomorphic to S3 or symmetric group of this well, equatory triangle. Okay, so today, first, let's try to prove it so that you will see for this kind of problem, if you have a really small number of elements, how can you form a rigorous proof about this kind of classification? Well, the idea of this kind of problem are always very stupid. But this is actually Although it's very stupid, but it's also the only way for us to find. Okay, so let's see. First, if G has order 2, 3, and 5, and 7, we already get that it's cyclic. Well, by the Lagrange counting theorem, right? So we only need to deal with, well, when order of G is 4 and 6. Okay. Well, the first one is trivial by Lagrange. And the second one, if G has order 4. Okay, if this happens, then, well, how can we discuss? How can we start? Sorry. Well, if you want to start, then maybe we should try to start at to discuss whether G has an element, because you know 4 equals to 2 times 2, right? So which means the element of this G can only have either order 2 or order 4. Okay? So if there exists an element A in G such that A has order 4, then we can say that, okay, we are done, right? Then that means G is equals to the generated group by A, the generated group of A, right? Because A is of order 4, so A to the power 0 is E, A to the power 1, A to the power 2, A to the power 3 are 3 different elements, and you have totally 4 elements, but G has order 4, so that's the whole group of G. So G equals the cyclic group generated by A. Okay, so, well, we have G is isomorphic to Z4. Okay, that's not very interesting. Now, if there doesn't exist a element A such that this element is of order 4, then that means every element in G, the order of your element equals to 2. Okay, what can we say about this? All the element has order 2. Well, that's not so hard, right? If all the element of this group has order 2, I think you did this kind of problems on your homework, right? You can prove that, okay, if all the elements of this group has order 2, then that simply means this group itself is a Abelian group. I forgot whether you have this problem in your homework or not. If you haven't, you can try to solve it.
Yes, we do.
Yeah, you do. That's great. So you can prove a lot of things by assuming that every element of this group is of order 2. But here we don't need to do a lot. It's very simple. A is of group where it's of order 2, and G contains 4 elements, so that means there exists B not equals to A, B not so equals to B, and B equals to, well, G. Okay? First, we take any element, non-zero element on G, and then we take another one. So of course, this G has 4 elements, right? Then we know that this G contains E and A and B, but this G must contains, well, okay, this G must contains, well, 4 elements. So what is the last element? Can you make a guess? What should be the last element? What should be the last element? We already find 3 different elements on G. How about the 4th one? Can you find it?
Wait, so if order is 2, it means that a squared is equals to e, or it means that
a squared equals to e, right? That's the mean. The order of a is 2.
Because I was thinking that, oh wait, can there be b squared equals to e, or
Well,
then it would be
you cannot have the plus. Well, you do not have this plus, right? This is a group. It only have one operation.
No, I just meant like, can we have like b squared equals to e? So that
B
b is the
squared
same
is also
as a.
equals to E because you have every element on G.
Oh, every element period
Third
2?
two,
Okay.
right?
Well, then we just have to have a third element with a period 2, right?
Yeah, you need to have the third element. So what should be your third element?
Like a multiplied by b, because
Yes, it should be A multiplied by B, right? Then you can find that this G formed by E, A, B, A, B is a group. Because, well, why is that? It's simply because you can say that, okay, this is a group. Why it is a group? Because any of these 4 elements, you take any 2 of them, you do multiplication, it is still among these 4 elements. Okay, so G is abelian. Well, G must be abelian, by the way. Well, why is that? Because AB is also of order 2, so that means AB squared equals to E, right? So AB equals to E, so that means, okay, well, if you multiply A inverse and you multiply B inverse, then it's equals to BA, and you know that BA inverse is A, B inverse is B, so it's equals to AB. Okay, so you know that this G is, well, you take A times B or B times A, they are both AB, right? So AB, well, so that means if you use A to multiply E, it's in G, it's inside of G. You use A multiplied by A, it's inside of G. Okay? You use A multiplied by B, it's AB inside of G. You use A multiplied by AB, is A squared times B is B inside of this G. Okay? Then you use B multiplied by E is B inside of this G. B times A is AB inside of this G. And B times B is E is inside of this B. B times AB is A, so it's inside of this G. Okay? And AB times E is AB, so it's inside of this G. AB times A is inside of this G. AB times B is inside of this G. AB squared is inside of this G. So this G is closed. It's closed. Everything can be represented by this A and B and A, B and E. So G itself is a group. Okay, so G must equals to this one. Okay, and you don't have anything that that is a repeated element. So this one is, of course, is well, isomorphic to this Klein-4 group. So we prove that if the order of G is 4, you only have 2 possibilities. One is, well, this G is Z4. The second one is this G is actually the, well, Klein-4 group. Okay? Now, we need to show that if the order of G is 6, then this G must be either Z6, which is well, an abelian group and a cyclic group, or is S3 when G is not abelian. And well, that also means that, well, the smallest or the, well, the smallest non-abelian group is S3. You cannot find a smaller one with less element. So let's think about this. How can we find G if we know that G's order is 6? Okay, So first, again, like we did before, if there exists an A in G such that the order of A is equals to 6, then we are done, right? G is this 6. It's isomorphic to A6.
Oh wait, sorry, quick question. I forgot how did we define S3?
S3 is equals to, okay, S3 is equals to, or this T is actually equals to, you have this group contains identity. It contains, well, actually you can write it as a group that generated by two elements. One is rotate this triangle by 120 degree counterclockwise, and another one is this kind of thing is a reflection, or the mirror. You do the mirror symmetry about this triangle, okay, and it's generated by these two elements. Moreover, you take cube equals to E, and F you take square equals to E. Okay, and you may have some other relation, something you may want to find in the future, like how can you compute R times F?
You said R square equals to E or R cube equals to E?
R cube equals to E, because
Okay.
it's like a rotation, like counterclockwise rotation, rotate by 120 degrees, because it's a triangle. It's a equilateral triangle, right?
Okay, thank you.
So if this G, if this G has an element of order 6, okay, then we are done. Now suppose there's no element on G has order 6. We know that 6 equals to 3 times 2, right? This group, well, this order of group is equals to 2 times 3. So that means, okay, the order of the element of this group could be either 2 or 3, right? Since we already exclude that if there exists an element is of order 6, then the rest of the situation we only need to discuss what if you don't have any element of order 6. Then that means all the element has to either of order 2 or 3. Okay, so what happened? So let's think about the easiest case. Okay, now suppose, since you have two numbers, suppose you do not have any element of order 3. You only have element of order 2. Then what happened? What happened? Well, if every element has order 2, then that means, okay, first, G must be abelian, but we don't really need that. The second, what we will find is then this group, this Klein 4 group, if you take two elements, A not equals to B and A, B both belongs to G, then based on these two elements, we can generate a group. And this is actually a subset of G, and itself is a group, so that means it's a subgroup of G, right? We pick up two elements from G, and these two elements are both not identity. They don't equals to each other. And from these two elements, we form a group, and it is a subgroup. This is actually a contradiction, right? Why is that? Why this is a contradiction? Why this is a contradiction?
Oh, because its order is 4, it doesn't divide 6.
Exactly. So the order of a subset must divide the order of this whole group. Subgroup must divide the order of the whole, right? But this is 4. This has order 4. It cannot divide 6. So this cannot be true. Okay. So that means there must, if there doesn't exist anything that of order 6, there must exist some element in G such that the order of this element is 3. Okay? That clear? So let's see. Then this element will form, well, again, we have one element, then let's try to generate a group. Okay? Is equals to A squared. It's a subgroup of G. Let's call it H. Okay? Now we can try to use our language of Cosets. Since this subgroup only contains 3 elements, right? So that means, okay, there must exist some element B such that B is not in H.
风吹花落泪如雨，雨会不想。
Hi, Long Chen. Well, anyway, well, we have an element that such that is not on this set H, right? So we can divide G into 2 parts. One part is H, another part is B times H. One subgroup and the corresponding coset of the subgroup. Okay? Well, so that means we divide the whole group into 2 parts, and then we know that, well, okay, let's try to think about, we have a B here. Then, well, what if we take the B square, because we want to find what's the relation between A and B. Well, at least we know that B square is not in BH, right? Why is that? Why B square not belongs to BH? Why B square cannot belongs to BH? Any idea? B is something.
Oh, because its order would be higher than 3? Or
we don't really know that. We don't really know what is the order of B, right? And from this, it seems that we cannot really find anything. Well, B square not belongs to BH is simply because if B square belongs to BH, then that means there exists some H in H such that B square equals to BH.
oh, and then we just make an inversion, so B is equals to H, so B is in the H, that's contradiction.
Yes, that's right. So that's a contradiction, right? So we know that B square cannot belong to BH. Okay. So that means B square must be in H. Great. B square in H. Well, B square in H. But we know that H only contains 3 elements, right? It contains E, A square, and an A. So this means if you want to find the relation between B and A, because as long as we know that, we know everything about G, then that means your B square can either equals to E or A square. Okay? There are 3 different situations. By the way, it seems that I forgot. Well, it's better for us to assume at the very beginning that okay, now maybe not at the very beginning, but at this moment, we need to discuss about this B, the relation between B and A. Then there are two situations actually. First, let's assume the easier case. Okay, let's assume some easier case such that, for instance, well, G is Abelian. For non-Abelian case, let's deal with it later. Okay. And first, assume G is Abelian, and then these three situations will become singular. Okay. After that, we'll assume G is non-Abelian, and then we can try to do more. So first, if G is Abelian, then we can get a warm-up. Then, okay, if, let's say, B squared equals to A. This one. Okay. If B squared equals to A, and we know that A is of order 3, and B is like the square root of A, something like that. Well, of course it's not, but you can imagine something like that. So that means probably B has order 6. Right? You can make a guess like that. So maybe you will try to check whether B generated a whole group of G or not. Let's see whether this happens or not. Let's see whether this happens. So B squared, which equals to A, and B cubed, which is equals to AB, and B to the power 4, which equals to B to the power 4, which equals to A squared, and B to the power 5, which equals to A squared B. If on this set, none of two are equal to each other, which means if on this set, it really contains 6 elements, then we know that it is actually G, right? Because every element are just an element in G plus they are not equals to each other. So we know that this is actually equals to G and G is actually Z6, right? So we need to check whether there are some elements that is, that equals to each other or not. Or we only need to check B has order 6, which means B to some power is not equals to 0 if this power is less than 6. Okay, so let's see. B to the power 1 is not identity. Of course, we choose B like that. B squared is A. It cannot be identity because we choose A not to be identity. B cubed is AB. It's not identity. Why is that? Why B cannot be the inverse of A? Why B cannot be the inverse of A?
Because then B has a period 2, and I assume it doesn't. Sorry, I'm kind of really confused at this point. I lost the logic chain somewhere in the middle.
Yeah. So here we want to say that B generated this whole G, right? So if we want to say that, we only need to say, okay, B has the order 6, right? If we want to say B has order 6, then the only problem for us is we only need to find, okay, B squared, B cubed are not equals to identity. It's not equals to E. Then that means B has to have this order 6, right? Then B generated a whole G. But now B cubed is A times B, right? If A times B equals to E, what does that mean? that means B equals to A inverse, right? Okay, B equals to A inverse. B does not belong to H. This is actually a contradiction because A inverse is in H, right? H is a group. So B cubed is not equals to E. So that means
Manipulations.
Mhm.
I said there was a lot of cool manipulation.
Well, there's no manipulation, okay? The only manipulation is you have to say that B generated a whole group. And that means there are only finite kind of cases you have to rule out. And now we try to rule out these finite many cases. Try to rule out. And well, we have to try very hard. This is just like the problems on your midterm, right? The problem that asks you to find, okay, what is F4? How can you find F4? It's exactly the same method, right? You try to rule out all the impossibilities and then you find that there is only one possibility. So B cubed, B squared cannot equals to E. B has to have order 6. Okay, then G is equals to the set generated by B, the group generated by B. Okay, any question? Now, what if B squared equals to A squared? Well, it seems not as good as before. It seems not as good as, okay, B is a square root of A, right? This seems like a thing that B has the same order of A. Well, so is that true? Or can we still say that G can be generated by B instead of something else? Well, if you do want to say that, that means you still want to say that B, well, this B has order 6, right? So if you do want to say B is of order 6, the only case you want to rule out is B cubed. If B cubed is not equals to identity, that means B has order 6, right? This is a logic. So let's check what is B cubed. Okay, B cubed is what? B cubed is equals to A squared times B. Can it be identity?
No.
Why?
The same reason as why AB cannot be E in the previous section.
Exactly. So if this is identity, then that means B is equals to A to the power minus 2, which belongs to H, right? So that means, okay, B is of order 6. So G is still generated by B. Okay? Last case. What if B squared equals to E? Well, in this case, you cannot say G is equals to the generated group by B, right? So we must play a little bit and try to see what kind of thing you can say about this G, because eventually, remember, we want to say that if G is abelian, then, okay, this G is actually Z6. So there must be something that can generate this whole group of G. If you try very hard, you find that, okay, then G must be generated by AB. B has order 2, A has order 3, then yes, probably AB should have order 6. Okay, why is that? Well, you only need to check AB squared is not equals to identity, AB cubed is not equals to identity, right? Then we are done. So why is not identity? AB squared is in a Abelian group. AB squared is actually A squared B squared. Well, in a Abelian group, this is awesome. Then B squared equals to E. This is A squared, not identity. A has order 3. This one, AB cubed, is equals to A cubed B cubed, right? A cubed, A has order 3. This is identity, is equals to identity times B cubed, which is B, not equals to identity, right? So we know that AB has order 6. Okay? Any question? Now, the harder part. Of course, this kind of proof is not necessary because, well, of course, if you don't assume your group is abelian, then you can still use the argument if B is non-abelian, right? For abelian part, I just want you to get some sense, get some feeling about how we can deal with this problem, okay? But now, if we do not have this kind of abelian assumption on G, what can we have? What do we have? Well, everything before are exactly the same, right? We don't really assume anything about whether it's abelian or not, right? So every argument are the same. If there exists an element A which is in G, A has order 6, then G is Z6. Now, if every element has order 2, you will have this is a subgroup of G, because from this argument, AB must commute. Well, AB must be, well, this AB equals to BA. Then this is a subgroup, then it's still a contradiction. And now, if you have some elements that is of order 3, then, okay, we can still do this kind of thing, until here, right? So, we still need to discuss whether B squared equals to A, B squared equals to A squared, B squared equals to E. 3 situations. If, well, B squared equals to A, we still have B must have, well, it must be order 6. Why is that? Because again, B squared not equals to identity, B cubed not equals to identity. We don't use the Abelian condition here. Okay? Otherwise, if B squared equals to A squared, then we still have, okay, B squared is not identity, B cubed is equals to A squared times B, it cannot be identity. Okay? So they are the same. The only thing that is different is the third case. If B squared equals to E, what happened? Now you see you have 2 elements that can generate it, G. One has order 3, A has order 3, another one has order 2, which is close enough to our set, well, S3, right? The only problem is we have to determine the, well, structure of this set, which means we have to compute the interaction between A and B. For instance, what is AB? What is BA? This kind of problem. Okay? Any question? So,
What?
question?
Wait. So yes, couldn't we, when we just started doing all that, like, did we have to really assume that, like, every, like, element has order 2 or blah blah blah? Couldn't we say at least 2 elements have order 2, because that would cover like more cases, but the proof would stay the same, so we'll have to do less work?
Well,
And-
if you only assume that only two different elements of order 2, that's totally fine. But the problem is then, okay, then how, I mean, you still have this kind of argument, right? If you have 2 elements of order 2, they are done, right? But then, other than that, what can you do? You can still, you have to still argue that, okay, A has order 3. There exists something of order 3. Something of order 3 is a key part. You have to discuss based on it. It can make this kind of subgroup slightly bigger so that you don't need to discuss 3 cases, 3 cosets. Make life easier. Okay? Which is why this may not be necessary, I agree, but this is still necessary. And as a complement, then you better assume that every element of order 2, because it doesn't change at all for this argument. Okay? Any other question? Okay, if no more question, then let's try to think what is AB, because that's the last step, right? As long as we can find AB and BA and this kind of thing, then we are done. We have the structure of the group. Okay, so we need to think about it. What is AB? First, we know that AB is not equals to H. Why is that? Why AB is not in H? Well, because you know that H only has 3 elements, right? AB cannot be any of them, right? So yeah, okay, that's fine. Then, okay, so that means AB must be in B times H, right? Okay, AB must be in B times H. What is B times H? Is B, BA, BA squared, right? Now it comes back to, case-by-case discussion, unfortunately. AB equals to B or B.
do we have to do that?
BA squared. Unfortunately, for a small number, you have to do it like that. There's no very powerful tool.
Can I ask a question?
Of course.
So, like, whenever I saw stuff like that, like, basically the logic we're using is pretty simple and pretty repetitive. Like, is it possible to write, say, a program which would do the same logical steps and solve this, like, finite cases for you?
Of course, it's possible because you are in a finite group and you only have finite many things to compare. However, sometimes you have to set up this program very careful, right? Because you must be able to find all the contradictions so that the computer can, the software or this program can tell, right? Otherwise, it will be a problem. right? Because for instance, here you cannot allow a squared b belongs to h and so on. A squared b equals to e and so on, right? All this kind of situation, you must set up as a stop, and then this program will become super long in some sense. And it is super complicated. You can try, definitely, you can try that. This is a most useful way to study a small order of finite group. And but I mean, if it is some higher order, something like order 12 or something, then you may need some theory that can simplify your argument a lot. There might be some theorem, and I believe there are some theorem, but well, even you have some theorem, you may find that okay, using that kind of theorem is like you are using something very, you're using an RPG to kill a fly, something like that. Okay, so sometimes you have to use something very complicated, but if you are not familiar with those kind of complicated theory, then you may still that it's very hard to do this kind of argument. Which is why, well, sometimes this kind of argument is good enough because, well, you don't need to assume you know anything. You just need to be careful enough. Okay? So let's do it. It's not so hard. Come on, it's not so hard. You only have this finite many cases. Here, we only discuss 3 kind of cases, right? Not so much. So first, if AB equals to B, we are done, right? Because that means A equals to E, which is a contradiction. So we only need to talk about AB equals to BA or BA squared. We know that if AB equals to BA, then, well, we go back to this situation, right? G becomes abelian. Because G generated by 2 elements, these 2 elements, they commute with each other. So G itself is abelian. So that means, okay, G is abelian. This, well, first situation, second situation. First situation, we get G is abelian. So G is Z6. How about the second case? The second case says that, okay, AB equals to BA squared. Oh, that makes sense, right? Then what we can get is G actually contains not a lot of element, right? It contains A squared. Okay, and BA, and BA squared, which is AB, with AB equals to BA squared. Okay, then you find that if you use a maps A to your rotation, the counterclockwise rotation maps B to your reflection, or the mirror symmetric reflection. Then you get a homomorphism from, well, G to S3 or T. And that's the end of the story. Okay? It's actually an isomorphism because it's for sure isomorphism. It's a bijection. Okay, then we are
done. Okay, so if we want to prove that something is isomorphic to something, like we have isomorphism theorems, and we just can build an isomorphism. But are there like any other tools, like say if you look at multiplication
at this moment,
and you're like,
at this moment you can only show it's an isomorphism because you have a bijection, you have a homomorphism, which is a bijection. This is the only way at this moment. Yeah. And well, to check it is actually an isomorphism or a homomorphism, you only need to check, okay, this phi AB is equals to phi A times phi B, which you will need this condition.
Also, then kind of similar question. What are the ways to prove that something is not isomorphic to something?
For instance, it have different order, or you have some different relation between elements, right? Because you get on this set, on this group, you have AB equals to B cubed times A. And on that group, you have AB equals to B squared. Two elements multiplied together, you get first element squared times second element squared. Then this is this will be a contradiction. Okay. By the way, so if we do have time, I'm not pretty sure at this moment, but probably no. If in the future you are interested about this kind of thing, then you will find that G is actually a free group. Well, you may not know what is a free group. It's actually a free group generated by two letters, A and B, and modulus the condition A cubed equals to E, B squared equals to E, and AB equals to BA squared. So that this is the reason why it's isomorphic to S3. Every group, you can try to write it as, well, some free group with some restriction. Okay, this condition can be seen as a restriction. Okay, that's how we do the classification of groups of order less than 7, less or equal than 7. Okay, any question? Well, then let's discuss another, well, this might be the most important concept in the group theory, which is so-called the normal group and quotient group. I know most of you do not like the quotient ring. Unfortunately, this is really useful, and on group, we also have those kind of quotient groups, which is also very, very important because it can help you a lot when you try to understand this kind of equivalent relation stuff. Okay, it can help you to understand a lot of groups. So, in order to do this kind of quotient stuff, it's just like the ideal we have in the ring. On a group, we should also have this kind of thing so that we can modulus it, right? Now, the candidate should be the coset. You try to define G modulus some group, some subgroup H, like to be something like all the coset, right? However, I forgot whether I mentioned that or not. This kind of thing, the set of all the coset of a subgroup H, it is not a group. Why is that? Because if you want to find the group structure on this coset, then what should you do? Well, you should define what is the multiplication of two cosets, right? For instance, AH and BH. But you can see that if G is not abelian, then this is definitely not AB times H, right? Even more, if you change the representative element A and B to be A prime, B prime, you do the multiplication, then of course you will not get A prime times B prime times H. Because element on this set should be A times H1, element on this set should be B times H2. If you do the multiplication, then of course it's not equals to AB times something like H3. right? Because you cannot commute with this H1 and B if G is not abelian, right? So here, in order to solve this kind of complicated situation, we must have another stuff which is more than a subset. Okay, this is something we call it a subgroup, which is a normal subgroup. A subgroup H, well, in G is normal if, well, you can imagine what should be the definition. You want to change the order of these two elements, right? How can you change that? There is a smart way to do that. If A times H times A inverse is a subset of H for any A in G. You take this kind of like a conjugate of this subgroup and it doesn't change this subgroup. Then we say it's normal. Okay? Or on the other word, for any A in G, any H in H, we have A times H times A inverse is still belongs to H. This guy, we call it the conjugate of H by A. Well, I hope this is not the first time you see this kind of operation on an element. You have seen this kind of operations in the matrix theory, in linear algebra, right? I believe you have seen this kind of thing, the conjugate of a matrix. Well, and we denote it as H triangle G. Okay, H is a normal subgroup of G. I'll give you examples, but before that, let me just write a remark. You see, this, well, AH A inverse belongs to H is what? It's just something like AH A inverse is equals to H prime, right? So if you multiply A both sides, you get AH equals to H prime times A. So this kind of conjugate is what? This kind of conjugate is just some kind of mimic or some analog of commutative, okay? It's some kind of replacement. Not really, but some kind of replacement of abelian. You can imagine it's kind of thing that is weaker than abelian, but is still good enough. Okay. So before, by the way, so talking about this conjugate, we can actually prove that conjugate of element is well, it's actually an equivalent relation between elements. Okay. Before I give you some example to see what is well, what is really a normal subgroup, any question about the definition? Okay, if no more question, Then let me first tell you, okay, if you do have this, maybe I'll just finish this proposition and then I'll give you some examples, because we try to define this normal subgroup simply because we want this G over H, this coset of H, be form subgroup, right? So first, I have to show you, okay, this does form a subgroup, well, a group. So if this you have H is a normal subgroup of G, then what we have is G modulus H, which is all this kind of well, coset of H is a group with AH times BH equals to ABH. You are able to do this multiplication between cosets. Why is that? Well, let's try to check it. First, we need to show that this multiplication is actually well defined, which means if you change this representative element, it doesn't change this multiplication at all, right? You cannot say that, okay, I take some other representative element, then the right-hand side just change. Then this multiplication is not good, right? First, let's check. It is well defined. Why is well defined? Say you have another representative element, AH equals to A prime H, BH equals to B prime H. You want to say that AH times BH is equals to A prime H times B prime H. It cannot, it shouldn't change. You can change the representative element, but the result shouldn't change. Okay? So that means, okay, A prime equals to, okay, A prime equals to AH and B prime equals to BK. HK are both in H. Okay? Then A prime B prime is equals to AH times BK. Okay? Now, let's play some trick here. You can see this guy. We want to say this A prime B prime times H is actually equals to AB times H. Then we are done, right? Remember, what do we want? We want to show that AH, BH, by your definition, by my definition, is equals to A prime H, B prime H, or AB times H is equals to A prime B prime times H. So that means we want to say that A prime B prime is actually AB times something in H. Right? This is what we want to say. So how can we write this A prime B prime as something like AB times H? This may not be easy, right? So how can we take this B and change the place of B and H? Any idea?
Can we take conjugate of it? So we take like instead of B we take H inverse BH, and so when we multiply
H inverse BH. Well, H inverse BH is not, well, what is that? What is H inverse BH? What do you mean H inverse BH? I'm sorry.
Okay, so like we said that it's a normal group, and so if we take any element for any element of G and any element of H, we can always find its kind of conjugate, right? So H is an element of G. So if we have B, we can always have an element which is equals to H inverse multiplied by B multiplied by H. And so if we kind of write B.
But be careful here. H is normal, right? So H is normal, that only means if you're trying to use B inverse or B times H, B inverse is in H, not the other way. Be careful. Right? This is our definition. You use
It's
other
straight
element.
inverse, right?
Mm-hmm.
Oh, no, that's what, like, the first one was what I meant.
Okay. Yeah, it's first. Well, you cannot use the first one. You can only use the second one. Come on. Because you can take some other element to do the conjugate of element on H. Right? To do the element on H. Okay, you got the correct idea. So basically, you see that this guy is B times H. B, H times B is actually equals to B times H prime, right? B times some other element, which is you can use B times B inverse times H times B. Okay? You insert an B inverse and B. Then what we do now is this term now becomes an element of H, right? You try to magically switch these two guys' position by putting some conjugate here. Then what you get is, well, this AB times something in H. So which means this belongs to AB times H. So that means, okay, it doesn't matter what representative element we choose. Is that clear? It's kind of you trying to use some kind of Abelian properties. But it's not really Abelian because when you're trying to switch the order of two elements, you just change one of the element. However, it doesn't matter. It doesn't matter. We still have this well, it's just something on this set. Okay, so this is well defined. You change the representative element, doesn't change the result you define. Okay? Now, it's easy to check. Well, how to check? You can check, okay, it's closed, this kind of operation is closed, every element has an inverse, it has an identity. Well, G over H is a group. By the definition of group. So we are done. So that means, okay, now we're still able to do the quotient of group by a normal subgroup. And moreover, now if H is a normal subgroup, then the index makes sense. Make more sense. We have this G over H is a group. The order of this group is equals to the order of G divided by the order of H. Which is why, well, we use this quotient notation. It's simply because you have this relation. So I think I should have a short break here and we will resume at 25, okay? Well, thank you. Yeah, sorry about that. I forgot to record it. So basically, we know that, well, Well, we know that the center of a group is a normal subgroup. And if you have a homomorphism, you have a group, you have a normal subgroup on this G prime, you push it back, it is normal subgroup. So this is also an example. You can try to find an example such that, well, you have a normal subgroup here, and the homomorphism maps it to a not normal subgroup on this G prime. Talking about the not normal subgroup, let me give you some examples about a group is not a subgroup is not a normal subgroup. For instance, let's say K looks like this. A diagonal matrix with, well, the determinant not equals to 0. Diagonal matrix, simple enough, right? It's inside of GL2R. This K is not, K is a subgroup. Any two elements on K, you do the multiplication, is still on K. Easy to check. But K is not normal.
But if we have like A equals to C would be normal, right?
Exactly. Well, so if A equals to C, this subgroup is a normal subgroup. And moreover, if A equals to C, well, is there any other proposition you have for this kind of let's call it H, okay, which is one number times it not equals to 0. It's again a subset. Moreover, you can see that it is a normal subset. But what else do you know about this subset, about this normal subgroup? As a subgroup of GL2R. Well, what is the center of GL2R? What is the center of GL2R? What are all the matrices that can commute with any other matrices? Well, if you try very hard in your linear algebra class, you can show that H is actually equals to the center. This is the only possibility for a matrix that commutes with every other matrices. Okay? And of course, since it is the center of this group, it is a normal subgroup. Okay? By the way, we haven't shown that this is not a normal subgroup. I have to give you examples. For instance, this one, and which is B equals to 1, 1, 0, 1. And you can check that BKB inverse is equals to 2 minus 1, 0, 1 is not in K. Okay? Any question before we move on? So there's a remark here I would like to mention. That is something I mentioned last time. Well, the biggest achievement in algebra during last century is so-called the classification of simple group. Now I can tell you what is the definition of simple group. If a group G has no normal subgroup, other than E and G itself, we call it a simple group. It's simple enough. It's more or less like a prime number, right? But this kind of group, well, until 2004, we get a classification of every finite simple groups. Okay. Okay, it seems that we get some idea about this normal subgroup of a group. Here, I would like to mention a little bit more about this normal group so that I think you will get a better understanding of it. That is some equivalent definition of normal group. Okay. Okay. So this is a theorem. The following are equivalent. Let's say, well, H is a subset of G. The following are equivalent. First, H is a normal subgroup of G, or A inverse is a subset of H for any A in G. Second, well, this is an inclusion, right? This is a subset. A inverse is a subset of H. However, the second says that, okay, it doesn't really need to say it's a subset. It's actually equal. But they are actually equivalent. And the third one is, well, if you take so-called the normalizer of H, it is G. This is so-called the normalizer of G of H is written as all the G in G such that G inverse is H, which is all the element on G such that it somehow can do the conjugate, give it back to your H. Okay. And the fourth one, every right coset or left coset of H is a left or right coset of H. Or which means, well, you gave me AH. There must exist a B so that it's equals to HB. Okay. These four kind of definition of property of subset, they are equivalent. Okay, let me prove it for you. The proof is not so hard, but here I just want to show you this kind of theorem such that this kind of the following are equivalent, this kind of theorem. How you can prove this kind of theorem. Basically, on this theorem, what we are going to do is we are trying to prove it by, we assume 1, it implies 2, and assume 2, it implies 3, assume 3, it implies 4, and assume 4, it implies 1. Then we say that everything is, they are just equivalent, right? Any question about the logic here? Okay, so let's try to prove it. First, we assume this one, H satisfies A times H times A inverse belongs to, well, it's a subset of H for any A. Then we want to show that for any A times H is equals to HA, or A times H times A inverse is equals to H. Okay, so let's first try to prove that. We assume 1 is true for H, then 2 is also true for H. Well, first, we know that AH, A inverse belongs as a subset of H for any A in G. This is what we know, right? For any A, this is true. So that means, okay, we can also multiply A inverse, both sides of this well, inequality of set, and A, both sides of this inequality of set. H is actually a subset of A inverse HA. Right? For every element here, well, it is A times H times A inverse, then of course it can be written as, well, because it's a subset of this, so it can be written as A inverse times H prime times A. So this is a subset of this. But we know that for any A of G, this subset, well, this inequality is always true. So this is also true for A is A inverse, which means this is also a subset of H.
Oh, sorry, just a quick question. I kind of forgot, why is second and fourth definitions, why are they different? Because it kind of...
The first one just say that
The second and fourth.
Hmm?
The second and fourth one?
The second and fourth one. The second one say that AH is equals to HA for this A. But the fourth one say that, okay, if you give me AH, I can find a B such that it's equal,
Okay.
right? So it's slightly different. Well, so we have, that means, well, you have this inequality. So this side is equals to this side, then of course H is A inverse HA, or H, well, AH equals to HA. Okay, so we can prove 1 implies 2. Now, suppose we have 2 and we want it implies 3. How can we prove it? 2 implies 3, so we want to say that, okay, AH equals to HA for any A. Then it is, well, then the normalizer is everything. This is trivial, right? Of course, this is true. Because every element is commute with this group, so of course it's always equals to H. Now we want the 3 implies 4. This is still trivial, right? Because that means GH equals to HG for any G. Then any right coset is equals to, you can find the left coset so that they are equal. This is still trivial. Right? Let's say over this. Lastly, we want to show that 4 implies 1. Why 4 implies 1? Suppose you have every right coset is also a left coset of H. Then how can we show that this, well, this must imply that? Let's see, okay? For any A in G, we have B in G such that, okay, AH equals to HB, right? This is what we have. So you have this, then what else do we have? Okay, first, you know that H is actually is a subgroup, so E is in H. So B is actually in H. Well, almost done. Right? So that means we got some relation between B and A. This is good enough. So there exists a H in H such that B is equals to AH. That means, okay, A inverse is H inverse B inverse. So H is what? H is equals to H is equals to, well, H times B is equals to A times H. So that means H is equals to A times H times B inverse. You can always, divide this B on this side, by B inverse both sides, even it is a group. Then that means H is equals to AH times, times H times A inverse. B inverse is H times A inverse. It's equals to AH A inverse. So AH A inverse is a subset of H. Well done. So the key point is you have to find the relation between A and B. Then you can try to write this equation as something we want. Right? Any question? Any question? No? Okay. Then let me try to talk a little bit more about this kind of normal subgroup, because then you will see something more interesting will happen. First, let me first state a theorem, which is quite normal, but you know that this normal subgroup, every kernel is a normal subgroup, right? But here, the reverse is also true. Any normal subgroup of a group can be seen as a kernel of some homomorphism. Okay? Well, why is that? The construction is actually pretty easy. You can try to find a phi maps G to G over H. And phi A equals to A times H. Then you can see that, okay, kernel phi is a homomorphism, and kernel of phi is equals to H. Okay? And last example that related to the theorem I'm going to talk about is, then we may also be interested about the product of groups. Okay? You may have two groups, and you may make the Cartesian product of these two groups, so that, as we did in your bonus problems in your midterm, well, you can define the operation on this set, like A comma A prime times B comma B prime is very simple. It's just A times B and A prime times B prime. Right? So which means if you gave me two groups, then what I will be able to do is I'm able to define a new group by the product of these two groups. And on this new group, you can see that we have slightly more normal groups. This and this are normal groups, normal subgroups. They are the kernel of the projection on G and the projection on G prime, which define as, well, I is from G cross G prime to G such that I, A, B is equals to A. And I prime is from G cross G prime to G prime, and I, A, B is equals to I prime A, B equals to B. Then the kernel of I is equals to E cross G prime. The kernel of I prime is equals to the E prime, well, G times E prime. This is an example of this theorem. Okay, you can see that, yes, probably some normal groups can always be seen as some kind of this kind of set, this kind of kernel. And probably you can imagine, okay, then that probably means you have this set and you take the quotient of this group, then you may basically get this, right? More or less like that. This is very interesting. And lastly, I would like to mention this kind of thing, which is something I mentioned last time. Well, when last time we talked about the Lagrange theorem about the counting, we mentioned the product of two groups, of two subgroups, right? Which is HK for any H in H, K in K. But as I said, this may not be a group. HK times H prime K prime, it may not be an element. It may not be an element of this HK as well. Right? So this is not a group. But as long as we know, as long as we've learned today about the normal group, you can see that we can somehow make this HK to be a group instead of just a set, instead of just a subset of G. For instance, we can say that if H is normal, or if K is normal, then H times K becomes, instead of a subset, becomes a subgroup. Right? So here is a proposition about it. This is so-called the direct sum, which is something you may have learned in your linear algebra class. You may not. Well, it depends. But this kind of direct sum is something I think very important when you learn geometry, when you learn algebra, or even when you learn the analysis. Because direct sum is kind of a decomposition of a space or a set. So let's say you have H and K are subsets, subgroups of G. Okay, then first, if H intersect with K, it's nothing but this E, which means they only intersect at 0. Okay, the product map P from H cross K now is not a direct, well, it's not this kind of multiplication. It's a Cartesian multiplication to G, defined by P of HK equals to HK be careful. Here, this P, is it a homomorphism? You take any element, any two elements on this H times K, then you map it to H times K, right? Is this a homomorphism? Because well, we have a natural group structure on the product of two groups. So it has a group structure. This G has a group structure. Then this PHK is it a group homomorphism? Is it?
Well, not. Wait, actually, yeah. Wait, actually, it is, right? Because the summation works, multiplication works for sure.
What is
and
summation? What is summation?
well, if we have like HK and AB, we have summation H plus A, K
How
plus
do you
B.
define A comma B plus C comma D?
Like you take it like dimension by dimension.
Remember, we are studying groups, okay? No addition at all. We only have one operation.
Oh, sorry. Yeah, okay. But then it's even easier.
Yes, it seems easier. However, it says that, okay, this P from H cross K, it gives you this kind of map. It has image is HK, right?
It's not a homomorphism.
It's not a homomorphism, right? Because as we mentioned, HK is actually not a subgroup. If it is a homomorphism, then the image must be a subgroup, right? The image is just a subset of G. But what I want to say here is this product map is injective. Okay, this product map is injective. Even it is not a homomorphism, but it's an injective. Then if either H or K is a normal subgroup, then this HK and KH are equal. It seems that you can try to commute with the product of two subgroups. Only, well, you only assume that it's normal. Okay? And HK is a subgroup of G. Okay? Now suppose you say that either H and or K is normal. So suppose H is normal. Okay? Then if you take the intersection of H intersected with K, it is still normal in K. So it's like you have a normal subset. The restriction on this normal subset is still normal. Okay? This is a subset of K as a group. And you can show that it is actually a subgroup. It is also a normal subgroup of K. Moreover, if you take the group generated by H and K, okay, generated by H and K. So which means it is the smallest group that contains H and K. Then is equals to HK is equals to KH, as we mentioned before. Well, this is just some kind of thing, say that, okay, it's a group. But then we don't see why they are interested, right? HK is just the smallest group such that it contains H and K. But that's not good enough for us. We need a little bit more, which is if H and K are both normal, and H intersect with K is identity, you don't have any intersection, then HK is a normal subgroup of G. Moreover, if you take this kind of product, it's actually isomorphic to the Cartesian product. If HK equals to G, that means H cross K is isomorphic to G. Okay? So which means we kind of do a decomposition of G by two normal subgroups. By splitting every element into two parts, and one part is in H, one part is in K. It's like a decomposition of G. Okay? And here you can see this is actually, well, you can also use the Lagrange theorems, the stronger version of Lagrange theorems, and you can see that, okay, if you try to compute the element of HK, yes, as long as this H intersect with K is E, is H intersect with K, oh well, on the top is HK. Then of course, yes, this is also true in this situation, right? This is just something you can understand it a bit better, okay? Something we mentioned last time, it agrees with our result here. Before we prove it, any question? So it's really like H and K are commute with each other. Moreover, you can split them and see them one by one. This theorem just tells us like that. Any question? If no question, then let's try to prove it. Okay. So first, let's try to prove A step by step. Okay. So for A, we just need to show that this product map is actually an injection, right? So what shall we prove? We just need to prove that, okay? If well, you have different this kind of HK, you shouldn't get the same HK. You shouldn't get the multiplication to be the same, right? So if H1 K1 equals to H2 K2, we should get H1 equals to H2 and K1 equals to K2. H1, H2 belongs to H, K1, K2 belongs to K. Okay? Injection, that means, okay, they must be, well, they must form the same pair. Otherwise, they shouldn't have the same multiplication. Okay? So let's see why this is true. Then you have this, okay. So what about we multiply H1 inverse both sides and K2 inverse both sides. But be careful, we have to multiply from the left for H1 inverse and from the right for this K2 inverse. Okay? So what we will get is K1, K2 inverse is equals to H1 inverse H2. Be careful, again, be careful about this order. Okay, this is very important. It's very easy to make mistake. Then, what do we have? We have one side, this are both on K. The other side are both element on H. So they are equal, that means it belongs to K intersect with H. Right? On one side it's in K, on the other side is in H, so it must be in K intersect with H, which is nothing but E. So that means K1 equals to K2, H1 equals to H2. Okay, so we are done. So P is injected. That clear? That okay? Then let's prove B. Let's try to prove B. We have proved A. So this P, this product map is an injection. Then we need to show that, okay, this, if one of them is normal, then HK is actually more than a subset. It's actually a subgroup, which is pretty nice for us. Okay, so let's say you have one, you assume one of them is a it's a normal subgroup. So let's say H is normal. Okay, H is a normal subgroup. Then H in H, K in K, and what we want to show is HK or KH. It should belong to, first it belongs to K times H. We want to show that it also belongs to, well, H times K. Okay, we try to prove this first. Then we prove it is a subgroup. Then we prove, okay, it's a normal subgroup, then it's equals to this one. Okay, first, let's try to prove that KH is actually equals to HK. Okay, so this guy is in KH. We want to switch these two elements, right? How can we switch these two elements? KH, we want to switch them, then that's not so hard. KH, if you want to add another term, then it's K inverse. Then this becomes something in H, multiplied by K, right? It belongs to HK because H is normal. Okay, so that means KH is equals to HK. Because any element in KH is an element in HK. Any element in HK is an element in KH, the same method. Then you are done. Okay, so HK is KH. Then, this is the first thing. Then, for subgroup, we want to show that this HK is a subgroup of G. How can we show that it is a subgroup instead of a subset? Okay, then that means we have to show that the multiplication is closed on KH or HK, right? You may have KH, you may have K prime H prime. Then you want to show that, okay, KH times K prime H prime is something in HK or KH as well, right? How can we show that? Again, here, what we want to do is we want to swap these two elements. Well, to swap these two elements is not so hard because we assume H is a normal set. So we play with this H. It's K inverse H K prime inverse H K prime, H prime times K prime times K. Then this part is in H, this part is in K, so it's in KH, right? So multiplication is closed. And we know that, okay, if you take the identity is inside of this multiplication of these two groups, of these two subgroups, and if you want to have KH inverse, it's also in KH because it's just H inverse, K inverse is in HK, and HK is KH. So that means inverse is closed. And you have E is in AK and H, so E is in KH. So KH is a group. Okay. Any question? Any questions so far? Okay, then, well, we also need to show that this H intersect with K is actually a normal subset. This is something, it's a normal subset of K. This is something not so hard. It's actually a normal subset of G, not only K. Okay, you can show it by yourself. This is easy. I'll not show it here. But last thing is, well, this HK, the group generated by two groups is equals to H times K. Well, this is also not so hard. First, you know that HK is actually a subset of HK, right? Because all the elements here can be generated by K and H, right? So of course, it's a subset. But meanwhile, you see that, okay, it is a group such that H is a subset of it, K is a subset of it, so HK is a subgroup that contains H and K. And this generated group is the smallest subgroup that contains H and K. So that means HK is equals to H times K. Okay. So we've proved B. Any question? Any question? Now C. C is the most interesting part, but the proof is not so hard. Now we know that H and K are both normal. We want to see HK is actually, well, isomorphic to H cross K. How can we show that? How can we show that? Well, okay, so let's consider this form. Let's try to consider whether this K, because you know that, well, KH and HK, they are kind of the same thing, right? So which means if you try to make this multiplication, it shouldn't be very bad. So let's try to compute, this is so-called the commutator of two elements, which is HK times H inverse K inverse. You can see that this is so, well, this is why it's called a commutator, because when it is E, then HK equals to KH, right? Then we know that H and K, they commute with each other. So which is why we call it a commutator. Commutator, and of HK. and it can measure how far away this HK are commute with each other. Okay, so if we look at this commutator of H and K, first it belongs to H, right? It's H times the H inverse conjugate. It's in H. But second is the conjugate of K times K inverse is also in K. So HK, H inverse, K inverse must be identity, nothing else. So that means HK equals to KH. Every element in K are commute with every element in H. Okay? So then we want to show that, well, first, HK is a subset of is a normal subset of G. Then that means, okay, we want to show that G, HK, G inverse is still in HK. Well, of course it's still in HK because it's G, H, G inverse, G, K, G inverse. So HK is a subset, is a subgroup, is a normal subgroup of G. Last thing, you want to show that this HK and H cross K is actually a homomorphism. It's actually a bijection homomorphism. Then that's very easy. We just need to check the nature multiplication. The nature product map is isomorphism, right? This is the last step. Because you cannot imagine how they can isomorphic to each other than you take anything on H, anything on K, and do the multiplication. So why first it is a homomorphism? Because you know that, okay, HK times, well, PHK is equals to, P H1 K1 times H2 K2 is equals to what? It's equals to, okay, is equals to H1 times H2 times K1 times K2. Since we know that everything on this K and H, they are commute with each other, right? So it's also equals to H1 times K1 times H2 times K2. Now it's really abelian instead of conjugate, right? So it's equals to P H1 K1 times P H2 K2. So this P, this product now becomes a homomorphism. And of course, it is an injection and on this map, it is, well, a surjection as well. So which means P is an isomorphism. Then we are done, right? Which means this kind of product and this kind of product, they seems very different. However, if H and K are normal, a normal subgroup, then they are actually the same. Any question? Any question? Question? Well, if you do not have any question, then let me show you an example. For instance, let's consider, well, two numbers such that GCD of RS is equals to 1. Then what we will have is ZRS is actually isomorphic to ZR cross ZS. Sometimes, since this is a Abelian group, so we don't really write it as as a product of ZR and ZS. We write it as ZR plus ZS. And we use a circle to cross this plus to mean this is so-called a direct sum. Direct sum means every element on this set has a unique decomposition of these two sets. Okay? It's like when you learn this linear algebra, every vector space can be written as the direct sum of the generators, right? Every linear vector space can be written as V1, which is a span of V1 plus the span of V2 plus and so on, and the span of Vn, where V1, V2 until Vn forms a basis. Okay, so this is a direct sum, which means any element on V can be written as a sum of this kind of space, of element of this kind of space, and this sum is actually a unique sum. The coefficients are unique. Okay. So why this is true? Well, this is true simply because you can choose the R to be 1, 0, 1, 2, until R minus 1. Then the RS has a normal subgroup called 0S to S, R minus 1S. This and this, they are isomorphic. Okay. Similarly, you have another normal subgroup of the RS, which is isomorphic to the S. And these two has no intersection. These two subspace, these two normal subset, the normal subgroup, they have no intersection, right? So which is why ZRS is isomorphic to ZR cross ZS, or ZR direct sum with ZS. Okay. You can find that, for ZR, ZS, they intersect with nothing, and their product, or their sum becomes every element on this ZRS. And a byproduct is, for any element in ZRS, you can write it as something times, R plus some other thing times S. And these two on ZRS are unique. Let's say this is T. This is A1, this is A2. A1, A2 are unique. on ZRS. Okay. I don't think this is true. You have to think about it for a while to see how they are unique, but you can get it from the theorem we have. It seems that I don't really have time for the, well, first isomorphism theorem. So I'll just write it here. And this first isomorphism theorem for groups is exactly the same as the first isomorphism for the ring. And I will not, for the group, I will not tell you what is the second and third isomorphism theorem. So we will just use the first isomorphism theorem. I'll just write it here and let you go. That is, you have a group homomorphism, and onto, then we will again have, okay, G over kernel phi is isomorphic to G prime. The way to prove it is exactly the same as the way we prove the first isomorphism theorem for ring. Okay, or the corollary is, okay, if you do not have an onto map, then G over kernel is isomorphic to the image of phi. Right, for sure. I'll just write down 2 examples, and sorry about that. I'll let you go. Sorry for delay, but I'll just finish it because I don't want to postpone it to next week. Sorry about that. So first example is, well, you can, based on the first isomorphism theorem, you can prove that R quotient ring, R over Z is actually, well, isomorphic to the group S1, which is the unit circle. Well, of course, you S1 equipped with cross, with multiplication. Okay, you can use R, map R to S1 to be phi, well, phi R equals to cosine 2 pi R plus I sine 2 pi, right? Then the kernel of phi is equals to all the integers. Okay, R equipped with plus, with addition, and S1 is S1 equipped with multiplication. Okay. Another example is, well, you know that determinant is from GL and R to R with multiplication, right? Then the determinant, the kernel of determinant is actually equals to what? Well, the multiplication identity of R cross is 1. So it's equals to SL and R. The special linear groups. So we get GL and R mod SL and R equals to R under the multiplication as groups. Okay, sorry about the delay. So I finish it, and we will discuss more about the groups next week. Okay, but maybe not so theoretical, but something with some particular set of groups may makes problem harder. You will see that. Okay, I'll see you next week. Bye. Sorry for delay. Bye.
Bye bye.
Oh, wow, that was a long